So today is trig day. Today and tomorrow are trig days. This was one of my favorite subjects in high school, but then I'm a nerd. But I think lots of people like trig, but don't like other stuff. Maybe. And this also has a lot of geometry, which is also all right. So today is going to be sort of the basic properties of trig functions. We'll solve a few basic trig equations. We'll see how to graph the trig functions, and we'll just do some general concepts. Okay, so we won't get to trig functions yet for a little while. We have to talk about angles and what we mean by angles, angle measure, angular velocity, and so forth. And then we'll get to trig functions probably after the first break sometime. Okay, so we're working in the plane. We don't have to be in the plane. We could be in any number of dimensions. But it's easy to describe these in the plane. So angles in the plane, you think of an angle as being a rotation of a half line around its endpoint. So a half line, also called a ray, has some vertex at its endpoint, and it extends straight out in some direction infinitely. And we imagine it rotating in some direction, where the vertex remains fixed, but the line is sweeping. Okay? The amount of that sweep is called the angle. So the sweep goes from an initial side in black to a terminal side in red. And the amount of rotation to get there is the angle, and we'll call this angle theta. Theta here is just some real number. We will theta is a signed quantity. So a counterclockwise rotation will give us a positive theta, and a clockwise rotation will give us a negative theta. So just in the case of angles in the plane, we will consider angles to be signed. So clockwise is a negative angle. So here, these are not the same angle, because the terminal sides and initial sides are different. All right. So every angle we can put into standard position. In standard position, an angle in standard position is one where the vertex is the origin, the initial side is the positive x-axis, and the rotation, of course, will be counterclockwise if it's positive, and clockwise if it's negative. So that'd be theta. That would be a positive theta. That would be a negative theta. We might rotate a lot more. So notice that the blue line, we start with the initial side and rotate one complete revolution and then an extra theta beyond that. We'll call that angle beta. That angle is different from theta. It's not the same angle. It's not the same real number. It's bigger than beta. But we say that these two angles are coterminal. What that means is they correspond to the same terminal side in standard position. So two different angles are coterminal if they look the same when you draw their terminal sides, if they have the same terminal side. Here's a third angle that's coterminal with the other two. It's negative. You go clockwise. Not quite one whole revolution, but then you get to the terminal side by going clockwise. So all three of these angles are coterminal. And in general, for every angle, there are infinitely many angles coterminal with it. And they all differ by a whole number of revolutions from the angle in question. Okay. All right. So how do we measure angles? The natural way to measure angles is called radian measure. There's also degree measure, which we'll get to, but degree measure is just more contrived. It's by convention. The mathematically natural way to measure an angle is called radian measure. Here's what we do. We draw a circle with some radius r around the vertex, around the origin in the standard position. We take the angle and we look at how much arc length on the on the circle is between the two sides. So we say this arc length is subtended by the two lines. We measure that length, we divide by the radius, and that gives us the angle. The reason why we divide by the radius is, well, we're not specifying what the radius is. If the radius increases, the arc length will increase proportionally, but the ratio will stay the same for the same angle. So this is clockwise. This angle will be positive because both S and R are positive quantities. This angle will be negative. Again, both S and R are positive quantities. So S is not signed. It's not negative if we go in one direction. It's independent of direction. It's just a length. S is always positive. The same with R. So if we go clockwise, we have to put a minus sign there. Okay. All right. So what if S is equal to R? Then theta, of course, is equal to 1. Well, that is the unit we're going to use. We'll call this 1 radian. But radian isn't really its own distinct unit. In fact, we can just say theta equals 1. In other words, radians are the default units. So we can think of angles as being unitless quantities, but their measure will be this measure if we do it that way. So that's counterclockwise. Okay. If S is equal to 2 pi, that's one complete revolution. 2 pi r. That's the complete circumference of the circle. In that case, here's the angle. It's one complete revolution. And so how many radians is that? So the terminal side and the initial side are the same. Well, it's the circumference divided by the radius, which is 2 pi. So 2 pi radians is 1 revolution. So a 1 revolution is what you get by going clockwise until you hit the initial side again with your terminal side. Or we go clockwise, in which case we get minus 2 pi radians for clockwise revolution. All right. So this, I think, should all be pretty basic to most people. Did we all have trig in high school? Anyone not have trig in high school? If we go half a circumference, that's when we go from the positive axis to the negative x-axis. Then that's pi r, then S is pi r, and so the angle is pi. So pi is half a revolution. If we go a quarter of a revolution, that's going to be then what? Pi over 2. But if we're going clockwise, what does that mean? It's negative pi over 2. So S here now is 1/4 of a revolution. So theta is negative pi over 2. Okay. So let's sketch these angles. Just to get a feeling for radians, we may not be used to radians if if calculus was a long time ago. So what does pi over 3 look like? Just use your fingers or your hand or your arms to show me. Yeah, it's right. It's like that. All right, so that's pi, so divide that into thirds. That's pi over 3. Minus 5 pi over 6. Where's that going to be? So I'm going clockwise. Tell me when to stop. Okay, good. Yeah, that's about right. So the thing you can do with angles, you can add and subtract angles. So, for example, minus 5 pi over 6 is, 5 pi over 6 is 3 pi over 6 plus 2 pi over 6. 3 pi over 6 is pi over 2. And 2 pi over 6 is pi over 3. So you can get there by first going clockwise pi over 2, and then clockwise again pi over 3. So when you add angles, you can visualize that by first sweeping out the first angle, and then for the second angle, use the terminal side of the first angle as the initial side of the second angle, and then sweep that out. And then the terminal side of that will be the sum of the two angles. And this works no matter which direction. So if you are subtracting two positive angles, you go in one direction, and then you'll come back. And then the net rotation is going to be the difference of the two angles. Sum of the two angles. Okay. So another way of doing this is it's minus pi, and then, so you go out minus pi clockwise, and then you come back pi over 6. So you go about minus pi, and now you just come back pi over 6. You get the same angle that way. Questions? So this is plus pi over 6, so it's counterclockwise. All right. So here we chop up the plane into 4 quadrants. These are what the axes do, the x and y axes. In the first quadrant, any terminal side in the first quadrant is going to give an angle between 0 and pi over 2. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4, so go in counterclockwise from the upper right. So quadrant 2, it's between pi over 2 and pi. Quadrant 3, pi and 3 pi over 2, and then 3 pi over 2, 2 pi. 2 pi is one complete revolution. And then the axes themselves, the positive x-axis represents the angle 0, which is also coterminal with one complete revolution, so it could be 2 pi, and it could be 4 pi, or minus 2 pi, and so forth. Positive y-axis is pi over 2, or anything coterminal with it. Negative x-axis is pi, and negative y-axis is not listed there, but it's 3 pi over 2, or minus pi over 2. Thank you. So, for any angle theta, there is an angle theta 1 that's coterminal with it that's in this range. So, this range, 0 to 2 pi, will include 0, but we exclude 2 pi. This gives, for every angle, this gives some coterminal angle. So this, you'll get all possible terminal sides through angles from 0 to 2 pi this way. All possible terminal sides are represented. And they're represented exactly once. So, in fact, this is unique. So for any angle, look at its terminal side, there is a unique angle, theta 1, in this range that's coterminal with it. Okay. All right. So let's do some more examples. Let's sketch the angles in standard position and find a positive coterminal angle whose radian measure is less than 2 pi. So minus pi over 2. That looks like that. So what's coterminal with it in this range, 0 to 2 pi? It would be 3 pi over 2. So it would look like that in the green. So in this case, theta 1 is theta plus a complete revolution. 9 pi over 4. Let's graph it. So one revolution is 2 pi, which is 8 pi over 4. And then you go another pi over 4, which chops that first quadrant in half. So what's coterminal with it? Pi over 4. Now, the coterminal angle is the original angle minus 2 pi. This will always be true. Coterminal angles differ by some integer multiple of 2 pi. So to get any coterminal angle, you add or subtract some integer times 2 pi. Okay. 8 pi over 3. Well, that's 2 pi, so express it as a sum of some complete number of revolutions plus something left over which is in the range 0 to 2 pi. So this is 2 pi plus 2 pi over 3. So that's 2 pi plus 2 pi over 3. That's theta. So we just take the 2 pi over 3, the green. And again, this is, you subtract a complete revolution to get theta 1. And let's see, minus 16 pi over 5. Well, this is 15 pi over 5 plus pi over 5. This is 3 pi. So go clockwise 3 pi. That's 3 half revolutions. So 1, 2, 3. 2, 3, like that. And then come back. Oh, sorry, no, I'm sorry. Continue on, because it's still minus. Clockwise, pi over 5. It's about like that, roughly. Okay. So what's theta 1 now? Four pi over 5. So that's pi, so that's got to be 4 pi over 5. So theta 1 is pi minus a pi over 5, because we're doing the same thing, and so that's going to be 4 pi over 5. And how many revolutions do these differ? 4 pi. So 2 complete revolutions. Questions? This is pretty basic. All right. Anyone think it's not basic? You can tell me in private if you're ashamed. That's okay. All right. It's degree measure. So this we're probably more used to. So in degree measure, we chop up one complete revolution into 360 equal parts, and we call each of one of those a degree. So one complete revolution is 360, or 0, because it's coterminal, so we start with 0. 90 degrees is a right angle. That's, in radians, what is that?
1/2.
Pi over 2. And 1/2 rotation is 180. Counterclockwise, so that's pi, and then 270, 3 pi over 2. Okay. All right. So, you just need to be able to convert from degrees to radians. So here's the basic equation. One revolution is 360 degrees, which equals 2 pi in radians. So this tells us how to convert between radians and degrees. So simplifying this, we'll divide both sides by 2, and we have 180 degrees is equal to pi. So this is the basic equation. If we divide by 180, then on the left we get 1 degree, and on the right we get pi over 180. So 1 degree is equal to pi over 180. Okay, I'm going to pound this into your brains. When you use degrees, you have to put that little circle there. Okay? If you don't put that little superscript circle, then I will interpret your answer as being in radians. And you don't want that. Okay. A degree is not a unitless quantity. It is actually 1 degree. 1 degree is actually, well, it is unitless, but it is equal to pi over 180. So you can think of that circle there as being a multiplier. Multiply by pi over 180, if you like. And that will give you the radians. Likewise, if you want to convert radians into degrees, 1 radian, well, divide both sides by pi. And 1 radian is 180 over pi degrees. So pi is what? 3.14. So what's 180 divided by 3.14? Well, it's a little bit less than 60. It's about 57, something like that. So a radian is much bigger than a degree. That's a good sanity check to tell you that you've actually multiplied by the right thing. You've either multiplied by this thing correctly or by that thing correctly. Okay. Questions on converting radians to degrees? Pretty basic again? Okay. Here's another thing. when you use your calculator, most calculators have two modes. They have degree mode and they have radian mode. Some have more than two, actually. Make sure you're in the correct mode for the problem at hand. I can't stress this enough. I can't tell you how many times I've just got a completely bizarre answer just because the calculator was using the wrong mode. Okay. So make sure you understand how to tell which mode you're in and how to switch modes. So do that now. No, you don't. No, not now. Do it at some point. Okay. So let's just exercise this a little bit. Express this in radian measures. So 4 degrees. Well, that's 1 degree times 4, and 1 degree is pi over 180. So you just plug that in, and you simplify, and you get pi over 45. So this is an exact simplified answer. When I ask for exact answers, generally the rule is always you simplify them as much as possible. Simplifying includes expressing fractions in lowest terms. So if the fraction, the ratio of two integers, if they have a common factor, you factor that out. 36 degrees. What? No? All right. 36 degrees. 36 times pi over 180. And this definitely simplifies to what? Don't go to your calculator, unless your calculator can do this exactly. Yeah, so it's pi over 5. Okay. So if I want an approximate answer, you should simplify your exact answer as much as possible before you go to your calculator. So use your calculator as a very last step. And the reason is if you don't simplify enough first and you start using your calculator, one thing, you might be using your calculator more than you need, and for another thing, you'll probably get more round-off error by doing that. Simplifying means you can cancel stuff out that won't cancel in your calculator. You'll just compound the round-off error to do that. So I can't stress it. I do stress. Simplify your expressions as much as possible before you compute an approximation. Enough said. All right, so let's go back from radians to degrees. So pi over 9 radians. Pi over 9. So that's 1/18 of a complete revolution. What's that in radians? Well, I'm sorry, what's that in degrees? Well, 1 radian is that, so it's pi over 9 times 180 degrees over pi. The pi's cancel, and I get that, which is what? 20 degrees. Notice that the circle goes where it needs to go. In fact, not only in the final answer, but we carry it along consistently in the string of equations. That's also important to do, because if you don't, chances are that you'll forget it at the end, go up significantly. This is what they, beat into our brains in physics class. That's where I got my undergrad. So I'm just passing on the baton to you, so to speak, hitting you over the head with it. So 3 pi over 20 in degrees, multiplied by 180 over pi. Pi's cancel again. 180 over 20 is what? 9. Oh, no, I'm sorry. What am I doing? Is that right? Oh, times 3. That 3. I forgot about that 3. Okay, 9 times 3 is 27. Okay. Plenty of time. So let's do a quick application. And I'm not going to do all of these slides. I'm going to skip some slides here because just seeing more and more basic stuff, we want to get to the good stuff. So So a circle has a radius of 3 feet. Find the length of the arc subtended by the central angle for an angle of 5 radians. So circle has a radius of 3 feet. Find the length of arc subtended by the central angle. So here's 5 radians. So 2 pi radians is 1 revolution, and that's 6.28. So 5 is going to be a bit less than that. It's going to be about there. We're asking for what is the green arc. So, okay. Well, r is equal to 3. That's the radius. Now we have this equation that we had on one of the very first few slides that said that theta is s divided by r. So we know what theta is, we know what r is, we just solve for s. So s is 15, and it's 15 feet, because our units of length are in feet. Okay. How about theta equals 18 degrees? That's 18 degrees. So what do? So use this equation again? No. And solve for s? Well, yeah, no. That's right. If we just did this, basically, if we just did this and divide and multiply r by 18, we're forgetting that theta is in degrees, and this equation gives theta in radians. So we have to convert theta into radians. So that's wrong. So this is for radian measure only. So we convert to radians first, and we get pi over 10 radians. Now we can plug that in. So s is 3 pi over 10, and what are the units of length? So it's not just 3 pi over 10. It's 3 pi over 10 what? Feet. Right. So units are important. Why don't I put that in? Here's one way to know you're wrong. If you multiply 18 by r, you can't do that if you are consistently putting that circle there. Then you really have to multiply 18 degrees by r. That circle tells you that it's not just 18r. It's not just 18 times 3. It's 18 times 3 degrees. So eventually you have to convert. It's actually 18 degrees degree feet. That's what it is. And so you actually have to convert into radians before you get it right. Okay. So just like carrying degree measure around, carry any other units around with you as well. So if r is in feet, then you could say here, instead of just a 3 feet. And that's probably even better. Okay. All right. So, one more example, and then we'll take an early break. So, an electric hoist has a drum 20 inches in diameter. It's used to lift a bucket. So, imagine this drum is rotating around the fulcrum there. And it's rotating this way, and it's used a bucket. How high will the bucket be raised if the drum rotates through an angle of 150 degrees? So it's 20 inches in diameter. So what's its radius? 10 inches. So the height of the bucket will be equal. So the bucket's being hoisted up like this. That distance that's being hoisted is the same as the arc length that a point on the pulley moves around the pulley as you rotate it that way. So in fact, h here is equal to s, the arc length. So converting 150 into radians, we get 5 pi over 6. And so theta is s over r. R is 10. So it's 10 inches times 5 pi over 6. Notice that I include the units there, inches, so there's no mistaking. Including units along with your calculations also helps prevent you making mistakes. Because if you forget, if you keep your units with you, you'll know that, for example, you have to divide by something instead of multiplying by something. You know, you won't make mistakes like that. Because if you do, your units won't be correct. So keeping units around also helps you avoid errors. All right, so this is 25 pi over 3 inches, or that's roughly 26 inches. All right, what if this drum rotates 3 complete revolutions? Then what's theta then? 6 pi, okay? So now theta is 6 pi, so S, using the same formula right here, S is equal to R theta, so that's 10 inches times 6 pi, or 60 pi inches. And so that's about 188.5 inches. Now let's bring time into the mix here. Oh, sorry, I gotta get this out of the way. It's not moving. Let's try this. Oh, now it moved. It just took time to think about it. Okay. So if it took the drum 2 minutes to make 3 revolutions, what is the average speed of the bucket? Well, what's speed? Remember from your physics class. Velocity. Distance per unit time. So it's distance divided by time. Total distance divided by time duration, that will be the average speed. So the total distance, we know, is this, 60 pi inches. And the amount of time is 2 minutes, so we just take 60 pi inches divided by 2 minutes. We get 30 pi inches per minute. That is a unit in rate of speed, or 94.25 inches in a minute. So, what do you think that is? Like, you know, how fast is that? Is that like that, or is it like that? It's going to be in between those two. It's going to be, you know, it's about 3 yards. So think of 1 minute in 60 seconds. Yeah, okay, all right. It's like a fast, slow cockroach. For a comparison. All right, almost done with this example. So if we bring time into the equation, then this introduces the concept of angular speed or angular velocity, and we will see this quantity again. Will change its name to angular frequency when we do waves. But it's the same basic quantity. Angular speed, the angular speed of some rotation. So think of something rotating around a central point in time. Its angular speed is the amount of angle it sweeps out per unit time. So it's not distance per unit time, it's angle per unit time. So it's going to be theta, the total angle it sweeps out, divided by the time it takes to do it. That's called the angular speed or angular velocity of a point moving around, rotating around a center, or some rotation, and we usually denote it by the lowercase letter omega, the Greek lowercase omega. So, in the last example, the angular speed of the drum was 6 pi radians every 2 minutes. So 3 revolutions every 2 minutes. So that's 3 pi radians per minute. Or, if you like, we could express this in revolutions per minute. So that would be 3 revolutions every 2 minutes, or 1.5 revolutions per minute, or RPM for short. Okay. Now, radians per minute. Radians is unitless. So angular velocity is sometimes is sometimes just described as 3 pi with no unit there, divided by minutes. So this would be, so you could write this as 3 pi min to the negative 1, which says you're dividing by that unit rather than multiplying by that unit. Okay? Because a radian is 1. 1 radian is equal to 1. So the radian as an explicit unit is purely optional. And so if we leave it out, the default angle is a radian. Okay. All right. Angular versus linear speed. So if the point is rotating at radius r around the center point, okay, then the amount of distance it sweeps out is the arc length. That's s. Okay. So its linear velocity is distance divided by time. So that's going to be s over t. And its angular velocity is going to be theta divided by t. So omega is theta divided by t. Well, we know how to relate theta and s using r. So s is equal to, using this equation, s is equal to theta times r. So now just take this and divide both sides by t, this equation here. And I get s over t is theta r over t. And then substituting, that's the linear velocity on the left, and on the right is the angular velocity times the radius. So we get this fundamental relationship between the angular velocity and linear velocity. The linear velocity is the angular velocity times the radius. Okay. All right. If I take a different radius, a bigger radius, then I get a new arc length, and I get a higher linear velocity. It's going to be s1 divided by t. And so v1 is bigger than v because s1 is bigger than s. But r1 is also proportionally bigger to r. Bigger than r by the same proportion. So in fact, I'll get the same angular velocity, even though the linear velocity is going up because the radius is going up. So here, theta is in radians. Omega is going to be in units of radians per unit time. Say radians per minute, radians per second, whatever. All right. Let's take a break, and then we'll finish this example. 10 minutes.
Plus, it's probably like 8 pounds of eraser shape.
I used a roller eraser yesterday.
We could drop this to a small hole and figure out how many frames.
Go look.
Yeah, high risk personality grade those first.
Dr. Finner, how soon
Yes.
after we take the test are we going to find out if we passed?
Let's see. You take it on Wednesday. You will find out probably by Friday, if Monday at the very latest.
'Cause we take it and then we start our.
I know. Yeah, you start your new thing right away.
No, we're on Christmas
Oh.
break. Christmas break.
Oh, that's right. Christmas break. I'm sorry. I'm
so
on the wrong.
people will have to re-study if they don't.
Yeah. You'll know the following Monday at the absolute latest, and that's that's like
Can we
the.
give you our email address? You just email us if we pass, so we don't have to stress that over Christmas.
As soon I will tell Wade, and as soon as Wade knows, he will transmit that information to you.
Wade said that he'll call you.
But if we do a retest, is it during Christmas break or when we come back?
He'll come back after Christmas break.
You know where that's going.
I suppose, unless you really want to take it during Christmas break. But
Friday, I might go to a baseball game just for fun.
That'd be fucked up. And
What are you doing?
Your tires.
so the exam's on the 19th, and that doesn't really leave much time for a retest. Unless you take it like right on Christmas or something like that. Nobody wants to do that.
Hopefully I get through it the first time. That's the plan.
What's that?
The plan is to get through it the first time.
That's the plan. That's the best plan. That beats everything else.
Okay, so we suspended for a week.
Ray, yes. Yeah. Colonel Ray, Ray, which was Army Commander at 112. And Army Commander. Yeah. And then left there and went over to the other side. Yeah. No, I was like, I noticed like, there's great things about that.
Little Omega. The internet on. This should, yeah, this should. Yeah, I had probably got 1 point off. What part did you get wrong? Quizzes don't count too much. Hardly any at all. I think the homework counts for more.
It's about like 3/4 full. See, I just have that. My dad would just have like, if he wants more than one, he just pops it up.
parents come to visit, they bring their purees and their coffee machine. Because they tried to buy me a coffee machine last night. I was like, I don't drink coffee. I'll give you coffee. And they're like, what you mean? I don't drink coffee. Don't buy it. So when they drive over there.
My mom comes to like, they want to farmer stuff. I know it's like, my mom's side of the family, they're coffee like all day long. It's like, you know, the whole thing, it's always coffee.
I chased the bond.
No, it's a point.
I think it was a good man. Like, my grandparents were Italian, so they always had coffee from something. No matter what time it is.
It doesn't make sense. I'm almost
It's
like 11 o'clock. I'm not going to drink coffee right now.
I forget about that. And then my mom offered me coffee every. Sometimes I'll have money in our. Like you can't talk about it. Then what it makes is it was so good and better like 11. It was so good.
vice versa.
This shit has to stop.
See, that's my drink of coffee typically increases exponentially when it's cooler outside. It's whatever.
Like here? When it turns about March.
Yeah.
Dude, it was like 110 this July. It was disgusting. I tried to golf one day when it was like 102. That was a huge mistake. Huge mistake. I was just like pouring sweat. I'm chugging water like, you know. And I was like, how would I get home? Because I'll probably pass out. So we get to the
use PT. Like I was okay at Bragg. There was always that 1 week at the end of July or August where PT was unbearable. If you trip PT in order to get an 85. But yeah, that started in like June. Yeah. And it went from like mid-June until like.
This year was bad.
Like where you just, it's like.
Even in Bragg, it was bad this year.
Dude, it was actually pretty mild here this summer. It was hot. Dude, it was hotter in Kansas than it was here.
It was like 105 this summer.
That's not that bad here.
That's disgusting.
I took 2 weeks of leave, went home to Oklahoma, and the coolest day that we had there was 109. And it was like in the 90s here.
God hates Oklahoma. It's
It hit home for me here.
I know what God hates it. It was like
I was going to say it was Fort Silver. Same thing. It's very good things.
I flew from Columbia to Seattle in mid-July. And left at 1:04 in Columbia at 7:30 in the morning. And I landed in Seattle at 59. And that road.
not 15 minutes stuff here. Like that vitamin C injection.
Yes. Then I was waiting.
Yeah, I wonder if I could sleep through volume.
But midnight should feel better.
Oh, yes.
Maybe like a little
It'd be like, no, I've been drinking my protein.
Oh, I've been eating oranges and all that kind of stuff. I wake up in the morning.
Good ass. Yeah.
So now they wake up when they fall down.
My biggest problem is that they don't
First week of
I don't use
Remember that.
2 hours.
One way to keep awake, pop one of these in your mouth without any water. You will be on fire.
So when I was a young man with 2 legs, I was the LDC to get another indicator, or was WLC. I remember I was on an ambush, and the tactician comes by and he's like, "Do you dip?" I didn't know, but he did. We were going to be there late.
You couldn't put any hours in.
I'm like, no, he's like, did you grab more free and just put the coffee in your mouth? That put me off coffee for a couple hours.
It's like an espresso roast too.
All right,
He has.
we're back. All right, so shall we finish up this example real quick? So now suppose the angular speed, I'll give you the angular speed. 4 revolutions a minute. What's the speed of the bucket? Remember, the radius is 10 inches. So what's the speed of the bucket? So we just use our equations and solve for what we want to solve for, which is S, which is the same as H. Well, it's actually S over T, or if you like, V. So V is 4 revolutions per minute. You got to convert that into what? Into radians per minute. The default angle measure is radians, so things have to be in radians. So 1 revolution is 2 pi radians. So just like a degree, a revolution is another angular unit that you have to convert to radians. So it's 8 pi radians per minute. So V is omega times R. R is 10 inches. So this is 8 pi times 10, and the 8 pi is in radians per minute, but radians is a unitless quantity, so we just ignore it. So this is this is the quantity this is in the units of 1 over a minute. And this is 10, that's in inches. So we get 251 inches per minute. So minutes is still in the denominator, and inches now is in the numerator. Okay, so 251 inches per minute. All right. That's about 4 inches per second. How did I get 4 inches per second? Guessing? You take minute and you substitute 60 seconds in for a minute. And it's in the denominator, so you divide by 60. That's how you do it. That's one way of doing it. So 251 divided by... The other thing is, this is inches per minute. We'd expect if you give a whole minute, you get a lot more distance in than if you only allow a second. So the number should go down. That's the sanity check. So a racing car moving at a rate of 80 miles an hour. The diameter of the front wheel is 2 feet. How fast is the front wheel rotating in RPM? So what's the RPM of the tire? So the car is going 80 miles an hour. So we've got miles and time is hours, and we want the revolutions as per minute. So we've got 2 different time units, and we also have 2 different distance units, don't we? We've got feet and we've got miles. So now we have to convert distance units and time units to get what we want. So let's consider a point on the wheel. So there's some point. So what is its linear speed if you fix the center of the wheel? If you just look at the center of the wheel, you move along with it, what's the linear speed of this point? Well, you'll notice the linear speed of the point is the same as the linear speed of the car. The reason is because think of when the point actually hits the pavement. Okay? Relative to the road, the point is still. It's at rest. Its speed is 0. But its speed with respect to the axis is its linear speed in this direction. So the only way that can happen is if the axis is moving in that direction at 80 miles an hour. So its linear speed relative to the axis is 80 miles an hour in that direction, but that's 0 relative to the road. So the axis has to be moving 80 miles an hour in the other direction for that to happen. So its linear speed around the axis, around the axle, is the same as the speed of the car. So V is 80 miles per hour. Well, so that's 80 miles divided by 1 hour. So now let's get this in terms of we're looking for revolutions per minute, and we're going to use the radius at some point, which is in feet. So let's try and get this in feet per minute, shall we? A mile is 5,280 feet. An hour is 60 minutes. Okay, so we can do some simplification here, and actually the denominator gets cleared, and we're left with 7040 feet per minute. Okay, V is omega r, so what that means is omega is what we're looking for, is V over r. So V is 80 miles an hour over radius. Well, the diameter is 2 feet, so the radius is 1 foot. So we've got this in feet per minute already. So now we get, so this is feet per minute in the numerator, so the minute drops down to the denominator, and we get 7040 things per minute. What are those things? Radians, right. It's the unitless, it's the phantom unit that disappears. So the ghost unit. So 7040 radians per minute. That's the angular speed. Question? That's radians per minute. We wanted revolutions per minute. So we have to convert radians to revolutions. Well, a revolution is 2 pi radians. So a radian is 1 revolution divided by 2 pi. So we plug that up here, and we get 7040 over 2 pi revolutions per minute. Simplifying that, 3520 over pi revolutions per minute. This is the simplified exact answer, and here's the approximate answer. About 1120 revolutions per minute. RPM. So, converting between distances and converting between time units.